All right, so in terms of where we're at, we've been looking at aldol type of reaction. So where kind of more specifically, we've been using aldehydes as the electrophile. There are some examples of using ketones. They're not that common. We did that one example with cyclohexanone. I think it was in the lecture. But generally speaking, a lot of these reactions are far more useful with aldehydes, which are very reactive. But of course, aldehydes can be a problem in terms of using them as electrophiles because we also don't want them to self-condense, etc., etc. So the way to get around this is we have to use a specific enol equivalent. In other words, we have to form something like this in solution. We have to kind of selectively form this, and then we can add our aldehyde and we get a reaction to occur. So we did this in class today. This is a lithium enolate, and the other way that we could do things is using a silyl enol ether to do exactly the same thing. They're just really, really bad nucleophiles. But to get them to work, we can pair them with an excellent electrophile, which is not exactly an aldehyde, but if we add a Lewis acid to it, we can supercharge this aldehyde and make it a fantastic electrophile, and so then this will react with the aldehyde in what it's a named reaction. It's called the Mukayama aldol reaction. We can get a carbon-carbon bond being formed like that. So we covered that in class. What I want to do now in this lecture is to just carry on with this idea of using aldehydes as electrophiles and give you some examples just based on other enolate types. So for instance, I'm going to give you an example that comes actually from the patent literature. I'm going to start with diethyl melanate, and we're going to react this diethyl melanate with a simple aldehyde. This one over here, 1, 2, 3, 4. It's a butanal, so it's a 3-methyl-butanal, and we're going to add a catalyst to this, and the catalyst, because it's coming from the patent literature, this is the catalyst. It's the amino acid proline. I'm going to say a little bit more about this just now. The solvent is DMSO, which is dimethyl sulfoxide. It looks like that, 2 methyl groups, sulfur, and a sulfoxide, it's O minus and S plus. Okay, that's a fantastic solvent. And then this is just done at roughly room temperature at 20 degrees Celsius. So this, as I said, it comes from the patent literature. It's a 2009 patent, very recent, for a synthetic process to make this compound over here. It's, they call it pregabalin. Not so sure how to say it. I'm probably saying it incorrect. Doesn't matter. Anyway, it looks like this. There's an amine here. It's actually chiral, but it's not going to affect what we can do at the moment. But this is used as to treat neuro pain, particularly after epileptic fits and those sorts of things. All right, so it's marketed by Pfizer, and this is a process, one of the steps in making this. It's not the whole process, but the product that we get out of this will be will look like this, because it's a typical aldol condensation. The only thing that we need to kind of look at, which is slightly different from this, 1, 2, 3, 4, counting it out. The only thing we need to be aware of this, and I want to just do the mechanism, because I know this is, if I had to show you something like this, all of this stuff here would confuse you. You'd get confused by, whoa, why are we adding an amino acid? The DMSO, you're probably going to think, oh no, what's it doing? Is it a reagent? What's going on? We need to learn DMSO as a solvent. It's not going to, we don't have to think about it in terms of the mechanism. It's not strictly true. Solvents are involved somewhere along the line, but we can, for all intents and purposes, ignore it. But we mustn't get confused by something like this, because you are expecting to add some sort of base to deprotonate here so that it can react with the aldehyde, and this doesn't look like a base. However, it is an amino acid, and it gets to act as both a base and an acid. More likely, though, this is just catalyzing the formation of the enol equivalent of this, which is actually very easy to form. Because we've discussed that there's resonance and conjugation that gets formed with that. So all that that this is doing is just catalyzing the formation of the enol form of this. All right, the malonic acid, dimethylmalonate, and this now can react with our aldehyde, and so that can go in, this can go here, that can go up, and the product we get is starting to look a lot like the final product that we need. Okay, so that's gone in. There's an H there, just leave it on. We formed a new bond. It's an O minus, and new bond, 1, 2, 3, 4, counting it out. All right, so we can now switch the protons around, and so I'm just going to do that very naughtily by scratching it out. Don't do this when you're showing me your answers. So we get an H over there, and now this can eliminate the mechanism. We're not having strong acid here, so maybe it's going to be E1CB, or maybe it's just going to be elimination. I wouldn't treat you too harshly on that, but let's just say that we do an E1CB mechanism, so that goes out there, so we get MEO O minus double bond. Let me see this. OME H, and that kicks back. Okay, so this was the E1CB mechanism. All right. I'm just showing you the mechanism of this. When I give you a mechanism in an exam or a test to do, I'll be a lot more explicit in terms of, I won't give you this sort of catalyst, which is a bit weird. Is it acting as an acid? Is it acting as a base? We're not too sure about that. I wouldn't give you something like that, but what I would be much more explicit catalyst. If it was a base, I'd expect you to be able to draw out this E1CB mechanism. If it was an acid, it's just an E1 elimination, which we discussed in class. So I think what I'm hoping is that the mechanism of this, as I've shown this to you and how this forms, should not have been anything surprising to you. We've already seen this type of reaction, getting a double bond after condensation of an aldol reaction occurring. The only thing that's important about this is we didn't choose to use LDA to specifically form this one equivalent of enolate in order to react with that aldehyde. And the reason for this is because this 1,3-dicarbonyl species is so acidic here, we can use a much milder version, all right, of a catalyst. In this case, we can actually use an acid catalyst in order to promote this reaction from reaction to go. And this catalyst is not going to interfere really with the aldehyde. That's the electrophile. And so in this case, it's just a fantastic partnership, all right? It's like doing great cooking, you know, you get the wonderful mix of flavors and everything just balances out very easily. So we're not having to use LDA. Going back to the cooking analogy, you know, if you're going to make creme brulee, if you want to make creme brulee and you want to kind of get the nice crispy caramel on the top, you use a tiny little blowtorch to do that. Now, on a cooking course, if they'd asked you a question, what are you going to use to caramelize the top of the creme brulee? And your answer was, I think I'm going to go get myself an industrial flamethrower. Well, that would be overkill, all right? And it's the same over here. You're not going to be using LDA. You could, all right, but you're not going to be, because it's actually so easy to remove that proton. In some cases, you just need a very weak acid or a very weak base just to get the reaction to a go. And in fact, there's another reaction which is almost identical to this, but it actually has a name to it. It's called the Knuvel-Nagel reaction. I'm going to probably misspell it over here. Knuvel-Nagel. All right, Knuvel-Nagel reaction, and what is going on over here is it's the reaction of a malonic acid, all right, not the ester, and you can take and the aldehyde that we're going to use is this one. Actually, this also comes from a 2010 patent. There's a nitrile there. All right, and we're going to condense those two. And Knuvel-Nagel reactions are very typically done in the presence of piperidine, which looks like this. That's piperidine, and also oddly enough, and I actually don't know why myself. I'll confess that a mixture of piperidine and pyridine, and the product looks something like this. Now, from the work we've done so far, you should be able to develop a mechanism of how we would go from those two to this over here. These are just acting as very mild bases. We don't have to be thinking about doing some weird and wonderful chemistry with this. Just follow the same sort of principles that have been applied in doing this type of reaction over here. The one difference being is that, like we had before, there's been a decarboxylation step. So I want you to try this at home. I want you to try and work out a mechanism for this. You can go to your textbook to help you, and you can go online to help you as well. But I think it'll be a lot more instructive if you just try this first by yourself and then go and see what the answer is online. All right, good luck with that.